we have been asked to approximate the value of the integral from 0 to 0.1 of e to the minus x squared dx with an error of magnitude less than 10 to the minus 8th. Well, the first thing I notice is that the function in the integrand results in a has a non-elementary antiderivative. I can't evaluate this easily using the fundamental theorem of calculus. So, dealing with a non-elementary integral makes me think to try to represent it with a series. So I'm going to start with the Maclaurin series for e to the x because I know it very well. Without too much effort, I can turn it into a power series for e to the minus x squared by replacing all of those x's with a minus x squared. Just thinking about how those exponents are going to treat the minus. And what I realize now is I have a series that looks a lot like the one I started with, but now is an alternating series, and all of my exponents are even numbers. All right, well, I can now do term-by-term integration to establish a series for the antiderivative. Well, I've written it without bounds here, so I'm going to start with a constant, an arbitrary constant, plus now we can go term by term and do some integration. X minus, well, x cubed over 3, plus x to the 5th. Got to divide by that new exponent, so I have a 5 times 2 factorial down there. And I can just continue in this fashion. All right, and if I think about that series, I could write that down as a sum if I wanted to. Is alternating. The first term, if I'm starting here, is positive, so minus 1 to the k. And let's see. On the bottom of that fraction, well, let's start with the exponent. I have x raised to an odd number going down, so let's say 2k plus 1, and we can just check that and make sure that when I plug a 0 in, I get a 1 out, and when I plug a 1 in, I get a 3 out, and I feel good about that. We're dividing by that same number times k factorial. 0 factorial, 3 times 1 factorial, 5 times 2 factorial, 3. So there's my sum, and writing that down lets me write down an nth term. So if I want to turn this into a Taylor polynomial to get a approximation, it would look like this. All the way until some last term, which would have this format. Minus 1 to the, I'll say n, times x to the 2n plus 1, all over that 2n plus 1 n factorial. And that tells me the degree of my Taylor polynomial is 2n plus 1. So I'm going to sneak back there and type in, write down a 2n plus 1. All right, so that's my nth term. Well, the reason that's important is this is an alternating series, and I know my error is bounded by the first unused term. So the magnitude of our error is going to be less than the first unused term of this in absolute value. So I can drop the alternating bit, put x in absolute value, and think about what the next term would be. Well, I'd have the next odd number, so I'd go up by 2 in the exponent, right? 7, 9, the next one's 11, they're all going up by 2. I gotta divide by that same number. And then I got an n factorial hanging out down there, right? I got a 4 factorial, 1, 2, 3, 4, 5 factorial, right? Just keep on counting like that. The next one would have a 5 factorial in it. And so I'm looking at that term. Now let's just make sure everything's working right. 0 factorial, 1 factorial, 2 factorial, 3, 4. Yeah, everything's counting up fine there, except for this is supposed to be the next term, so that should actually be an n plus 1 down there. All right, glad I caught that. I knew something was off. I had to think my way through it. All right, so now I have a bound for my error. And now, to figure out what's going on, I'm going to imagine that I let x be as big as x can possibly be. Well, for the problem we're looking at, the biggest x can be is the top bound. I'm integrating from 0 to 0.1. The largest x is 0.1. Well, I don't think I really need that absolute value anymore. All right, so now I'm looking for the value of n that makes this less than 10 to the minus 8th. Well, I'm going to do this by inspection, and I've already gotten a head start. I've typed my error bound here, 0.1 to the 2x plus 3, because my calculator doesn't understand what an n is, divided by 2x plus 3 times x plus 1 factorial, and I'm going to use my table of values to find where the first value of n is that gives me something less than 10 to the minus 8th. I have my calculator set up to ask me what independent variables I want to put in, so I put in 1, 2, and 3, and I didn't have to go that far. At n equals 2, this calculation is already less than 10 to the minus 8th. In fact, at that point, it's 2.4 times 10 to the minus 9th. So now I know the degree of my Taylor polynomial, right? N is equal to 2, and if I come back here, the degree of my Taylor polynomial is 2n plus 1. So I am looking for t, 2n plus 1 would be the 5th degree Taylor polynomial. So I'm going out to here. Well, I guess the way I've committed to doing this right now is with my antiderivative being a c plus x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial would just be 10. Well, that's my antiderivative. Well, now I would just be evaluating it from 0 to 0.1. And at this point, I know I can drop that plus c because it would cancel out. And so my antiderivative, well, any antiderivative, evaluated from 0 to 0.1. Let's see, I'm going to get 0.1 minus 0.1 cubed over 3 plus 0.1 to the 5th over 10. And I can type that into my graphing calculator and get an answer, and let's just see what happens. And that might be small down there, but I get 0.9966667. And I know that I'm within 10 to the minus 8th. So anywhere 1, 2, 3, 4, 5, 6, 7, 8, rounding to about there would give me a really good approximation of that definite integral.